Hi, welcome to our video on LiDAR, light detection and ranging. So LiDAR is an active remote sensing technique, and it works by pulsing a laser from an aircraft down to the surface and then measuring how long it takes that laser pulse to come back to a detector on board the aircraft. So that two-way travel time can be turned into a distance or a height of the aircraft, which can then be turned into an elevation. And we can use those elevations to construct very high resolution digital elevation models, or DEMs. Now, a digital elevation model is basically just a raster or a grid of elevation values that can then be rendered by a computer to actually have show topographic relief or show a landscape. In this case, this is a very high-resolution LiDAR image of Paris. So one of the huge advantages of LiDAR data is that the pixel size of the digital elevation model can be incredibly small, down to even just a half meter or less, which lets us capture extraordinary detail about changes in elevation and the shape of a surface, whether it's a city or a natural landscape. So here's an example of that. Here's a typical 10-meter resolution digital elevation model of a hill slope in California. You can roughly see where the peaks are. You can roughly see where the river valleys are, but you can't see any of the finer detail. For example, you wouldn't even know there was a road snaking along this hill slope. But once we get this 1-meter resolution LiDAR data, we can suddenly start to see details like roads and gullies. So it's hard to overstate what a revolution LiDAR data has been for Earth scientists, to suddenly be able to see the landscape in such incredibly beautiful detail. So in this video, we're going to do three things. We're going to first look at how LiDAR data is collected. Then we're going to look a little bit about the format that LiDAR data comes in. And then we're going to finish with a few slides on how you might create a digital elevation model from raw LiDAR data. So here's what a LiDAR system looks like. As I said, it's an active technique that involves shooting a laser beam out of an airplane. Okay, so you got to have an airplane, or in some cases a satellite. On board that airplane is a GPS unit. And so that allows us to keep track of the exact location of the airplane as it's collecting this elevation data. The airplane also has an inertial measurement unit. This tells us exact information about the pitch or the roll of the airplane at any given time. Obviously, an airplane is not perfectly stable, so we need this inertial measurement unit to tell us how exactly the airplane might have been tilted at any given time, and therefore which direction the laser was pointing at any given time. And then of course we have the laser itself. Commonly this would be an infrared laser, a 1064 nanometer, but also green lasers are used, which are more effective at penetrating water. And so the basic pattern of data collection is this. Laser pulses are being pulsed at an incredible rate, thousands per second, and the laser is basically sweeping back and forth as the plane is flying forward. So you end up with a pattern of laser shots or of elevations that is not at all grid-like. It's actually very much a zigzag pattern, and we'll talk later about how we turn that in to a digital elevation model grid. And then finally we need ground control points. So things like this GPS. We need to know certain locations on the Earth's surface very precisely so that we can then ultimately turn these elevations back into a map. Now, one benefit of LiDAR is that the footprint is often very, very small. It's usually a circular footprint. And for most terrestrial LiDAR, the small footprint LiDAR, it would be less than 30 centimeters, so a pretty small little laser spot. However, there are certainly applications that use large footprint lasers with spots ranging well into the hundreds of meters. One example of a large footprint laser is the Mars Orbiting Laser Altimeter, or MOLA. This was an instrument that flew on board the Mars Global Surveyor satellite, and it orbited Mars from 1996 to 2001, basically collecting LiDAR data the whole time. And it had a spot size of about 168 meters. So this was a fairly coarse resolution LiDAR data. But it produced this gorgeous map. It literally mapped the detailed topography of the entire planet of Mars. So it's hard to overstate how important this is. Much of what we know about the hydrology of Mars, the volcanoes, the lava flows, so much of that information wouldn't be possible without having this really detailed topographic data set. Now, it's common that we collect two types of data with LiDAR. One is the range distance, and that would be the distance from the aircraft to the ground, which is determined by this two-way travel time of the laser pulse. And that's how we get elevation. The second type of data would be intensity. So this is really the fraction of photons that are returned back to the aircraft. Maybe you send out 1 billion, and maybe you only get back 500 million. So the number of returning photons determines the intensity of that radiation, and that's actually controlled by the material properties of the surface. Some surfaces are really good at absorbing the laser wavelength. Other materials are really reflective. They don't absorb it. So for example, a lot of LiDAR is done with an infrared laser, and vegetation reflects very, very brightly in the infrared. So we tend to get high intensity returns off vegetation. And so this intensity information can actually be used to be diagnostic of surface materials in some cases. So let's look at a couple examples here. We'll do range first. So range is determined by the two-way travel time, okay? And these photons are, of course, traveling at the speed of light, or c. And the range then is given by the speed of light times the travel time. So that gives you distance in meters divided by 2, given that it was a two-way travel time. And now let's look at intensity. So here's an example of intensity. This is an intensity map of an airport collected using a 1024 nanometer laser. So this is an infrared laser. And what you can see here is that the black asphalt of the runway is very good at absorbing this infrared wavelength. So the intensity returned is very low, and the asphalt therefore appears dark. In contrast, the grass around the runway is vegetation. It's very reflective at 1024 nanometer, and so it appears very bright. So you can see that there's actually compositional information within the intensity of the LiDAR return. Now, it's also important to note that reflections of LiDAR light on the ground can be very complex, and it's quite common that each outgoing laser pulse would yield multiple returns, okay? And so typically in a LiDAR data set, each data point may actually not have a single range. It may have multiple ranges that correspond to up to 5 different LiDAR returns from the surface. So let's have a look here. Here comes the laser pulse. It first hits this branch, then this branch, and so on until finally it hits the ground. Each of these collisions bounces back a pulse back to the aircraft. And the aircraft is recording a continuous signal in time. So it sees each of these returns as a pulse of photons at a given time, okay? And typically what the processing has to do is establish some background level and then say, okay, anything above a background is going to be categorized as a discrete pulse, okay, or a discrete return. And the hope is that the last return is typically taken as the return off the ground. Now, bear in mind, the number of returns and the complexity of returns also provides information about the surface material. So you can imagine if you shot a laser beam down onto a bedrock surface, you might get only one return, and that would be off the ground. Same if you shot it off the roof of a house, you might just get one return off the roof. In contrast, if you shoot it into a forest of dense vegetation, you're almost always going to get multiple returns. And sometimes you can actually invert that information to learn about the structure of forest canopies, for example. Now, importantly, it's very common to take the first return and the last return and turn them into very different products. And so here, a digital terrain model is actually shown here in B. And this is what you might call a bare earth digital model. This is made from the last return, okay, which is supposed to be from the ground. So in theory, this should show you information about the surface texture of the ground, okay? So that would be a digital terrain model. This one, A, is a digital surface model. This might be a digital elevation model that's made from the first return, which is typically going to be off of that tree canopy, right? So take a look at these. These are from the exact same area, okay? The digital surface model shows the height of trees, then it shows areas that have been clear cut where there's fewer trees, and then it shows an alpine meadow here where there's no trees at all. So this gives us this amazing rendering of the forest canopy, right? The digital surface model. Whereas the digital terrain model gives us this, sees through the forest and gives us this amazingly detailed rendering of the actual land surface, okay? So you can start to imagine how powerful these different things are. The geologist might care a lot about the digital terrain model, whereas the biologist might care more about the digital surface model. Okay, so now that you have an understanding of some of the basics of LiDAR, let's talk a little bit about the format of the data. And you start to get a sense that there's a lot of information that needs to actually be stored. And LiDAR data is typically stored in a point cloud format, okay? And that usually has a .las extension, a LAS file. And we can think of the LAS file as, basically a table that has all these different entries in the table. So for example, it has the X and the Y coordinate of each shot location. It has the intensity, and in this case it has the return number. So this would be perhaps the first return, the second return, the third return, how many total returns, and importantly here, it would also have the classification. So it's quite common that LiDAR data is classified in terms of whether it was deemed water, whether it was deemed forest, or other categories. So for example, here's a little clip from our own Addison County LiDAR data set. And things are broken down into all the different classes here. So it had a total of 1.5 billion LiDAR shots. So these are going to be big files. 424 million of those were deemed ground, okay? 193,000 were deemed water, okay? So you'll find that different LiDAR data sets have different classification categories, but almost always the data will show up having been classified during the processing stage. Okay, so now let's say you want to take that LiDAR data and make it into a digital elevation model, or a DEM. Remember the fundamental problem we're facing here, which was that the LiDAR shot points are not spaced on a regular grid. They were collected as the laser rastered back and forth, zigzagging. So they tend to have a zigzag pattern. And of course, we would like to convert that zigzag pattern into a grid, like a raster, And the way we're going to do it is we're going to need to resample the LiDAR data. So we know the coordinate of each of these laser shots, and we're going to resample those into a gridded model. And so just to remind you, we're going from a point cloud data into a grid or a raster format here. So what's the basic way this works? Basically what you do is you start with an empty grid. You decide, okay, I want a grid of 1 meter by 1 meter pixels, and each of those pixels then gets a coordinate. And so then you can basically overlay your grid pixels with the actual shot points, okay? And then you do a search. You basically say, okay, I'm going to start at this pixel, and I'm going to search for LiDAR shots in some radius r of my pixel, okay? And then I'm going to take, maybe I find 3 or 4 LiDAR points. I'm going to compute an inverse distance weighted average. I'm basically going to compute a weighted mean elevation from those LiDAR shot points that were in my vicinity. And in the case where I don't find any LiDAR shot points, I would first end up with a no data or a null pixel, which I would then interpolate. All right, so let's look at a little example of this here. This isn't perfect, but it's pretty close. This is an example of how you might get a mean elevation by taking an inverse distance weighted mean. All right, so here's P. This will be the pixel value that we're trying to fill, okay? And each of these red dots or red pluses represents a LiDAR shot point. So let's say we did a search within maybe 2 meters, and we came up with 3 shot points, okay? One of those was 23 units away, one was 58 centimeters, and one was 35 centimeters, okay? And we don't know the elevation here yet. This is what we're trying to figure out. And we're going to do a weighted average of these 3 LiDAR shot points, okay? 230, 320, and 580. So those might be the elevations, perhaps also in centimeters. Okay, so how do we do this? How do we do an inverse distance weighted? Here's the formula. The elevation of the shot point is given by the sum of all the elevations times 1 over their distance from the actual point P. So what does that mean? It means that if you were further away, if D was bigger, then that means you're going to be multiplying Z by a smaller number, and you're going to get weighted less. And then we're going to divide all of those by the sum of 1 over D, okay? So in this example, we'd have 230 over 23 plus 320 over 58, 580 over 35. We'd sum those on the top, and then we divide them by the sum of 1 over each distance. And so the key thing is that this point right here, 230, is going to get the highest weighting because it is closest, right? And this is going to get the lowest weighting because it is furthest away. And so in this example, this was an inverse distance weighting, or a weighted mean. And in this case, we use the weights to be 1 over r. It might be more common to use a weighting of 1 over r squared. Now in this case, if you think about it, this is actually penalizing for distance even more. So this is weighting faraway points even less, basically. And so just to finish this up, what controls the resolution of a DEM that you could actually make from LiDAR data points? And obviously what controls this is basically we'd love to have the smallest pixel size that we possibly can. However, if we have pixel sizes that are too small, we may end up with a lot of empty or null pixels, right? And so this experiment shows LiDAR data that had an initial shot density of about 3.6 shots per meter squared. Okay, so each meter squared had 3.6 laser shots on average. Okay, And here's 4 different attempts to make DEMs. Here's a 1/4 meter DEM, a 1/2 meter, a 1 meter, and a 2 meter. When we attempt the 2 meter DEM, or 2 meter pixels, we're only left with 471 null pixels. So basically, almost every pixel had at least one shot point in it. When we get down to 1 meter pixels, we're only left with 666. So still, most pixels had a shot point. If we try to go to 1/2 meter, we end up with 60,000 null pixels. So here we've gotten to a point where a large number of the pixels actually didn't have a shot in them, or didn't have a shot within the search radius. And so obviously the optimal size here is going to be someplace between a 1/2 meter and a 1 meter pixel resolution. And just to reiterate that, obviously people want smaller pixels because that may record more surface detail. However, the minimum pixel size you can get is limited by the shot density, which of course is ultimately controlled by how the data was collected during the data collection. Awesome. So that wraps up our video about LiDAR. We talked a little bit about how the data is collected, what the format of the data is, and then how we can create a digital elevation model from that data. Thanks for listening.